Welcome back to the Deep Learning Big Data course. So this is the second part of the practical lecture 10.1, the Deep Learning Driven by Big Data. So I will just do a small recap of what we saw in the previous part. So if you remember, we started from, to recap a bit of the machine learning fundamentals. And we saw that, with machine learning, what we're aiming is to learn from data that we have in order to derive and to build an analytical model, right? So, and we can do this by just learning from data, right? Without knowing the exact formula a priori at the beginning. We saw this very nice example, right, with the flowers, where we have to detect if it's a type of flower 1 or type of flower 2. So, and this was possible to be done with already, let's say, not so complicated machine learning models. So what we saw is that it is fundamental that we have the data, obviously, but also that we have patterns in the data that we can detect and learn, right? And a very important aspect is that once we learn, then we should be able to generalize, so to be able to identify then when we get new images, right? So from samples of different flowers, to be able again to make the right decision. So basically, we revisit the perceptron model, right? We identify the limitation of this model, and we saw that this is basically about the type of problem that you have, right? So if you have a linear separable problem, you can do it with perceptron, because at the end you just build a line, right? So decision boundary. But of course, once you have more complicated problem like the XOR problem, this cannot work anymore. So you need a more complex architecture. And that's exactly where we started to talk about multi-layer perceptron. So we also talk about a lot, the importance of the features, how the features are relevant, and the key part in order to be able to then to do the final classification in an efficient way. So after that, we basically started also to wonder, okay, but what is the best architecture that can deal when you have basically data that are images in input, right? So we started to consider the type of properties that we have, right? So the locality and the translation invariance, and how we can use these properties to build a particular network. And we basically saw that with convolutional neural network, you can embed these properties and then build a very effective classifier, which can learn features by itself automatically and hierarchically, right? So here you see the exact part. So we started from a fully connected neural networks here in the left side, and we passed through this different type of architecture, which is especially designed for images, where you can identify three main components. Of course, there are many more, but this is something that you will realize when you start to make your hands dirty with this, with the code and with the different properties and parameters that you might have. But as a very general overview, you should remember that talk about a convolutional neural network. You of course will have a convolutional layer, right, where we do the application of these local filters all over the image, where we extract feature maps, right? Which then these feature maps are learned hierarchically and reduced, hopefully maybe with pooling layers. And at the end, you will arrive to a point where you will be able finally to do a final decision, so the classification. This can be done by using, again, the fully connected layer, as you can see here in the image. So this is what we saw. And maybe here you can see another example, maybe to clarify a bit more with a concrete example from a car. And you can see here that you start from raw data, and as a user, as a scientist, if you want, you don't need to take care of creating the features. I mean, if you were to do it by yourself, you would know that the feature that characterizes a car is that you have a mirror, you have the beams in front. You know exactly what are the features that matter in order to say this image contains a car. You don't need to do that. This can be done by the network, by the convolutional neural network. And here you see the exact property that I was referring before, the hierarchy, right? So where in each of the layers, you will be able to see different type of features built upon the previous So you see this hierarchy property. Okay, now I would like to zoom a bit, a bit back before I continue with convolutional neural network, in particular, how we can optimize the weights of convolutional neural networks by talk about, again, more generally about deep learning, right? So deep learning is basically emerging as a leading artificial intelligence technique, right? As you see here, probably already the scheme, where deep learning is a subfield of machine learning, which is a subfield of artificial intelligence. And why this is happening? Well, there are three main reasons. So you have the first reason, which is connected to this, basically the capability that we have in computing. And this could be, for instance, high performance computer that you're studying in this course, but of course also other types of computing, cloud computing, quantum computing, and many different types. So of course, this is a very important aspect to that made this happening, made this emergence of deep learning. Then of course you have a very another important aspect, which is the access to large volumes of data. So this is very important, especially with internet nowadays, and of course all different type of sensor that you can imagine. And I will give you a concrete example from my research field, which is remote sensing and Earth observation, where basically I will show you that we have a large variety of sensors, satellites, but also different type of platforms like airborne, drones, you name that. So a variety of sensors that are able to collect a lot of data. And of course, this data, we have them, but we need to be able to process them, right? So, but we have the data. That's the important thing. And they are most of the time free, especially in Earth observation. And then, of course, you have the emergence of basically new algorithms that can enable robust training of large-scale deep neural networks. So this is also very important, because at the end, okay, you can have a network, a very deep neural networks. You can have a cluster with GPUs, but you still need to understand how to exploit and how to use efficiently the cluster with many GPUs in order to train a deep neural network. And this is exactly the thing that you will see in the next lecture, how to speed up the training of convolutional neural network, for example. Okay, so basically you see these three components here below deep learning. So you have data, free data, a lot of data available. You can rely on computation based on different technology, different computing paradigms. And of course, you have also a extreme amount of research in the theory of deep learning, machine learning. This is a field that changes every day. Every day there is a new paper or new methods. So it's also very difficult to stay updated, to be honest. Right. So let's now see why. And here I want to a bit motivate why high performance computing is very relevant, again, for deep learning in particular. So you probably already know maybe some popular data set like ImageNet, but basically what is happening now is that each research field is working now a lot to generate new data sets that are in this case, for instance, labeled. So you have a lot of experts label the data that can be used then in a supervised learning setting from that can then exploit convolutional neural networks, for instance. And this is also what is happening in my domain. So we have a lot of new data sets with more samples and more complicated tasks that can be used to train this deep neural network. And of course, this also at the end require what? More computation. And this is what high performance computing is there for us. Then, of course, we should also consider that there is a lot of research going also in different directions, not just supervised learning, but also different type of learning. We can mention self-supervised learning, unsupervised learning, reinforcement learning. So these are all other type of learning where basically you do not rely on a training set where all the samples are labeled. So imagine your training set with all the images from the flowers. In this case, you might be in a condition where you just have only the images, but you don't know the label. And this is the typical situation in real application scenarios. Because if you think about labeling is expensive, costs a lot. You need to have a lot of time and money spent on that. So a lot of research now is going in the direction to try to be able to basically learn from the data without labels. So this is called unsupervised learning. And if this becomes more successful and become more effective, then you can expect basically that you can use infinite amount of data, right? Because then you don't need to rely anymore on the labels, which means again that you need more computation. So high performance computing will be there, to rescue. So here you see also another trend. So there is a trend that is now happening in in deep learning, where basically bigger is better. So models are growing a lot. Actually, you see an example here. You started from perceptron in 1960, and you can see here how the models became bigger and bigger. And of course, this requires, again, more computation. And here you see one example, for instance, from the natural language processing, a recent model that has been trained, GPT-3, which, these are the two generations, actually. You have GPT-2 and GPT-3, and you see already the jump of the number of parameters, the weights that now this model includes. So we're talking about now 175, for instance, billions of parameters. And then you can imagine that in this case, high performance computing play basically a crucial role in order to train such a big network. But maybe you also heard about, AlphaFold, which was a problem that was basically a 50-year-old challenge in biology that was also solved with deep learning. But of course, also their HPC was there as a support. Okay, so these are all motivation that should also make clear why HPC is important, was a key important also factor to the rise of deep learning. Also here, maybe it's a bit more advanced, but basically we can expect that this trend will continue, so that this model will keep growing. Because we kind of realized that at the end, bigger model will be able to still generalize. So we will not overfit it. So I will not enter into details, but there are studies that showing that, if we continue growing anyway, we will still be able to generalize even better. And which means, again, bigger models, right? Which more weights to learn, which means more HPC. And finally, also, let's think about the strategies, right? So if you probably start to realize that whenever you need to design a convolutional neural network or an artificial neural network, you have already so many parameters that you need to decide. How many hidden layers do I put? How many neurons do I put? What is the activation function that I use? And so many, right? So imagine that now this is actually the step where you spend most of the time. Like if before in classical machine learning, you would spend most of the time to create the features, right? Feature engineering. This is done, basically solved by deep learning. But what now you need to work on is to define what is the best deep learning architecture that you can use, right? And this requires a decision of all these parameters. And of course, now there are strategies that try to automatize this process. And this is basically under the umbrella of auto machine learning. And very popular now methods are the neural architectural search, where basically, you define a set of architectures. And this could be many. Like here is an example of a free data set, if you want, which is called NASBench 201, which basically includes more than 15,000 candidate architectures. And each of it has to be trained and tested to see if it is the right one for your problem, right? And you can imagine that this is very computational expensive. And this is exactly the place where, again, high-performance computing can really help a lot, right? To avoid that you spend 90% of the time on this project just defining and looking for the best parameters or the best hyperparameters of the network. Another important thing is that to realize, and also realize being at the Jülich Supercomputing Center in the last years, is that the recent high-performance computing architectures and parallel programming in general, they're actually being influenced by the rapid advancement of deep learning and hardware accelerators. Because at the end, the classical workflow that used to run on the HPC system, and this could be numerical methods based on physical laws, various scientific fields are now becoming more heterogeneous, which means that the availability of machine learning methods, deep learning methods now require higher memory, more storage, more networking capabilities, and of course also more optimized software and libraries to deliver basically the required performance. And this means that now supercomputers, and you probably heard about modular supercomputing architectures, and now think about in this direction, where the hardware that is inside is basically try to meet the requirements of deep learning models. And here you see, for instance, an example that back then, I think last year or 2 years ago, Microsoft announced a new supercomputer with the vision of AI. But this is happening all in Europe and everywhere in the country. So this is very important. And also think about that, supercomputing is not just helping the training, but can also help the inference part, where you do the prediction. Because at the end, if you think about if you have a huge model, you still need a lot of computation there in order to be able that, the data will pass through the big network to do the final prediction. So at the end, HPC is there, and it will boost all these new developments. Okay, now let's stop here and let's again zoom a bit more into details about what we were referring before. And so if you remember, we were talking about convolutional neural networks for classification, and here again another view, if you want, where you define the exact two-step, right? So the feature learning part and the classification. So on the left side, you have the feature learning, where you have the convolution, the pooling layers, where you try to really understand what are the better parameters, weights that you can use to generate feature maps. And then you have the final part where you can come back to the fully connected architecture, where you can basically now express and do the final classification. So this is what we saw already, and these two steps are inside the single architecture, so you don't need to care about this. Once you define the architecture, this is something that will be done automatically. Of course, with the cost of the computation, as we just saw. But until now, basically, I showed you what are the building blocks of a convolutional neural network, right? So at the end, I told you a lot how the architecture is, what are the different components, but I didn't tell you how exactly we can learn these weights, right? Because at the end, this is what all matters. We need to find the best weights that fit our problem, and this is what we will see now. And for doing this, of course, we need to talk about backpropagation. So the question again, what are the weights that should be modified out, right? So what are the weights that will allow us to make correct classification? So basically, we're trying to understand what are the connections that should be intensified or reduced in order to have less error possible in the output. And so the backpropagation algorithm is the most fundamental building block in your network, and of course the first thing that you will learn whenever you start to work on this domain. It actually was introduced in the 1960s, so it's quite old. And basically, the algorithm is used to effectively actually train a neural network to a method that is called the chain rule, right? So in simple terms, basically what you do is that after each forward pass through the networks of your data, the backpropagation performs a backward pass while adjusting the model's parameters. So you will adjust the models based on something that you see at the end. And what you see at the end, and this is the final step that you see here in the bottom part. So the final step in the forward pass is to basically evaluate if the predicted output Y against the expected or the desired output D that you have in your data set, right? So you have your training data set with the labels, so you know exactly what should be the output, so the desired output D, so you can make this comparison at the end. So this evaluation between the expected, the desired output and the output that Nectar does will be evaluated through a cost function, and here we will call it the loss function. And this could be, a simple mean square error, or also more complex like cross entropy. So it's not important to enter now into details, but it's important to remember that once your data has passed an actor, we will have this step where we need to verify if what the actor put as an output is actually what we expected or not, right? And what we can say is that now, based on this loss, the model automatically knows how much to adjust the parameters, like in order to get closer to the expected output in the next iterations. And this happens exactly with the backpropagation algorithm. So you will come back and you will adjust the weights, and you will continue this interacting until this loss value will be as small as possible, right? So you want to be sure that this becomes as minimum as possible. And when you reach that, you're sure that now what your nectar is predicting is actually the desired output that you have and that you know because you have the labels again, right? So here we're working with the labels. So basically here you see again sketch of the algorithm. So you have the three phases. The first phase, you pass the data, and this is called forward propagation phase, where the information goes to the nectar, the data goes to the nectar, and then you have the the checking with the loss function, and the information that the amount that we get there will then influence the way how the weights are then adjusted in the backward propagation phase. And this is something that will continue over and over. So you see, basically we are talking about loss optimization, right? So we want to optimize and basically find a way interactively to update the weights over the training data. And what we want to find out is the empirical loss, so it's minimal, right? Of course, we are now working on this training set, right? So we call it empirical because this is the minimum inside this particular training set. And you can imagine now here that what we're trying to, of course, to adjust, right, are the weights. And you see here that this is the most important parameters when you need to think about how expensive it would be to compute this optimization, right? Because if you have more weights, actually, which means that you will have to really, go through all the weights and find all these weights all the time at each iteration, right? So this is what we are trying to do. So let's now make an example. Maybe visually it will be a bit easier to understand. So let's imagine we have a very simple nectar. Here we have two weights, so BW0, BW1, and we have the loss, like the value that we get out of this function. So what is the objective here? The objective here is to find the lowest point in this landscape that correspond to the minimum. So how can we do that? So if you remember, we will start with the nectars, which has random weights. So we don't know, it could be 0, it could be anything, right? So we will start basically in a random point. This random point, for instance, could be this one. So in this case, we are not very lucky. We are kind of almost on a maximum. So what we need to do is to find our way through the loss in order to find which is the right direction to move, which will bring us to the weights that identify the minimum, right? So what we will do is to compute the so-called gradients. So we compute the gradient at this local point. And in this landscape, the gradients, what tell us is basically the direction of the maximum. So it basically gives you it tells you where we grow, right? So what we need to do is to basically take the opposite direction. So we are sure that, we are walking down the hill. So we can do that. And this is exactly the step, all the iteration that I was talking about. Every time we come back, then we can do a movement in a direction. And we will continue until we get, hopefully, the minimum. And the minimum, you see, identify the best value of parameter W0 and W1. So here now we found what are the best parameters, and now we can use these parameters to, to use the model for to do the prediction, to do the final job that, we were trying to achieve. So if you want to know more details about, how this step works, also with the rule of chain, I recommend you this video. This is very interesting, and it gives you a very clear example where you can also, write down on a paper all the parameters and see how the backpropagation will work. So this is something that you can have a look. And it was very interesting. Okay, so to summarize, what we discuss is the backpropagation algorithm. So again, we start from an actor that has random weights, right? And then we have a loop, right, where we need to compute every time the gradients, which basically explain us and give us the direction, right, to move into this into this landscape. And you can imagine that this is the most computational part, especially when the number of weights is very high, right? And this is the point where you will see in the next lecture. It's the point where GPUs plays an important role, and based on this component, you will understand what you can actually try to parallelize here in order to speed up this step. But I don't want to spoil it, so I will leave it there. And what we know exactly is that whenever we compute the gradients, then we will take the opposite direction, right, to walk down the hill. But how long so the question here is, how long will be the step, right, to go down the hill? And this depends, of course, of how trust you have in the loss function. And this is basically regulated by the so-called learning rate, which is just a factor here that you multiply, which will basically determine how far you will walk down the hill. And this is another parameter, again, that you will have to learn or determine, basically. And you can see basically 3 different cases. So how this can really affect also the type of learning you do. So if you take a learning rate which is very small, which means that you don't really trust to move in the direction that the gradient tells you, you will basically end up just doing small steps, but will never reaching the actual minimum. On the other hand, you could have a very big learning rate, but this could lead you to a situation where you just, you jump around the loss whenever actually arrive to the minimum. This is also not really good. Of course, you might imagine a very nice situation where you will have an adaptive way where the learning rate will adjust at every step to do, different type of direction, and you will maybe do first a big step at the beginning, and then you will just go slow and slow until you reach the final minimum. So of course, this is also a lot of work in progress. If you want a lot of papers, a lot of way to optimize this, and which of course will take many lectures. Right. So in the final part of this lecture, I would like to give you a concrete problem about big data. So here I have a very general lecture or like slide, if you want, about big data, and this was in a very buzzword some years ago, which has been then substituted by deep learning, and probably now will be substituted by quantum computing, maybe, or something else. But anyway, this is something that you should know, because at the end, it's still true. At the end, if you look at data, what you should consider is not just their volume in terms of megabytes, gigabytes, but you should also consider different type of properties that this data might have, right? And this is what this V definition comes. So the volume, velocity, variety. And I will give you a concrete example with remote sensing data to be more concrete. But basically, you have different properties which basically define if the data are big or not. And here you can also refer to different resources, and each book, each article will give you a different, let's say, or different perspective. But let's take a concrete case. So basically my research field is from the remote sensing, and to basically in a nutshell, remote sensing is every time you perform a measurement without being in contact with the with the object itself. And I think that the easy way to explain this is to just to show you this example here, where you can imagine you have a satellite above the atmosphere, and this satellite will record the energy which is emitted by the sun and then reflected back by the different objects on the surface. And you can record this energy with spatial sensors, which will generate particular type of images, which are not just RGB, right? And the idea is that once you record this information and you prepare this data, then you can use this data to try to automatically discriminate different type of objects on the surface. Because the idea is that each object will reflect or will emit the energy in a different way on different wavelengths. So you have a lot of properties in the back that will help you then to identify the different objects. So these are actually the features. So the wavelengths, you will see the bands are actually the features that you can use to identify different objects. So this is just, the key message here is that images are not just a single picture taken from a simple camera, but is a result of a very complex process. Happens between the surface and the atmosphere. So if you want, this is again simple sketch of the process where imagine you have the lights coming from the sun, which will go through the atmosphere. So you see that there is already an interaction here. So the remaining part will go to the surface, will then interact again with the objects, and some of the light will be retransmitted back and go through the atmosphere again, and this will be recorded by a sensor, which then can be transmitted back to a receiving unit, and basically is there the place where you can start if you want machine learning, deep learning. So once you have the data, then you can start to analyze them. So remote sensing is basically, you can see that it's not an invasive method, right? So you can use it by just using a platform, and you have many different platforms. You have drones, helicopters, balloons, satellites, and of course the decision of which platform you use, it really depends on the type of application and the type of accuracy, or the resolution that you want to use in your data. But anyway, if you just look at the satellite, you can see that it's a perfect view because it's repetitive and consistent. So you can always use it to monitor some particular events that occur in a particular region of the Earth. And then you can see here just a subset of particular applications, but there are of course many more. So this is just. So maybe here just to give you an idea. So you're probably more familiar with an image that have 3 channels. So the red and green and blue band, that would be the left one here. Here you just see the single bands, but of course, if you combine them, you will see, of course, the colors. And what we have is different type of images. So we can have the hyperspectral images where you can see that actually a pixel doesn't have just 3 channels, but it can have many, many more. And here we're talking about hundreds of channels. And the interesting fact is that if you see, so these are like pixels that belong to different classes. So you have gravel here, bricks, and trees. And you can see here how by looking different portion of this the spectrum, you can see that value changes according to the type of classes you consider. So if you want to distinguish trees between these 2 different classes, you can basically consider the features that are on this particular type of the spectrum, because you can see that here the pixels have completely different values than the other 2 classes. And you can see here that these are features that comes from a particular sensor that you can already use to basically prepare the data before you do the discrimination between the classes. Of course, some classes will have very similar features and patterns. So here, of course, you will need more sophisticated models. Okay, so let's now talk about again this concept of big data and why remote sensing has big data. So at the end, this is not just due to basically an extreme volume of data. As you can imagine, here you see a picture of how many basically satellites we have now and how many will be launched by 2025. So this is something very impressive if you want. But of course, you also need to think that remote sensing data are also multi-source, multi-scale, high-dimensional, and they also connected to dynamic states, linear characteristics of the type of application you're considering. And the important thing is that many EO programs, governments, and space agencies are actually opening their archives, which means that satellite data are available to everyone, which means an open source policy, very important. Of course, we should also consider that present and upcoming mission will actually use different type of technology, like small satellites constellations, which will have even higher spatial, spectral, and temporal resolution, which means that we will have just more data from multi-source data, so more data. And of course, we should not consider also other sources, right? So here I just show you satellites, but we can also have airborne sensor. But of course, also we are starting to using different type of data, like social media, also very important, machine-to-machine communication, also crowdsourcing. So you see at the end, we can really exploit many type of data, and this basically makes them more big. So it basically, you see that in the challenge, right? At the end, what we want to do is to find ways to extract interpretable information from this amount of data, right? And of course, possibly in real time, but this is another aspect. So in Europe, we have Copernicus, which is the world's largest single Earth observation program, which basically, use this free and open data policy, which means that the data are free, and you have a large family, which is of satellites, which is the Sentinel space, where each satellite basically mounts a particular sensor, which is designed to record particular type of information. So this is, you can already see probably in this, evaluate yourself how much data we could collect already with this family of satellites. And here also I included the video if you're interested, where it explains a bit more about the Copernicus program. But basically, to conclude, is if you look again close by the definition. So if you look about remote sensing data, why these are big data? So of course, we will talk about the volume, and this is clear, right? So we have so many sensors that we create and a lot of data. But you need to think also about different types of properties, like velocity. Velocity means that, for instance, nowadays, especially satellites can pass over the same place on the Earth every few days. For instance, Copernicus Sentinel-2 can pass over the same area every 5 days, which means that you have every 5 days an acquisition on the particular area. And this, of course, allows you to do a lot of analysis, but this is another property that tells you this is a big data. Then, of course, you have variety, right? Variety means that we have different sensors. So I show you that we don't have just RGB images, we have also hyperspectral images. But then, of course, we have also different type of data, like radar data, LiDAR data, many different types. And each of them has particular properties. And of course, this makes more complicated, especially when you want to think about how to fuse all this data in a single deep learning model. And this is a very complicated approach and challenge. Other two important V's, of course, are veracity and value. So veracity means that the data you might get might be corrupted, right? You don't know exactly what happened, for instance, in the interaction with the atmosphere. So you need to consider that there might be outliers. So you cannot use straight away the data. If you remember, there was this pre-processing step that you need to consider whenever you want to apply machine learning or deep learning models. So this is something that you always need to consider. And yeah, and of course, very important, the value, right? So at the end, we can, Earth observation provides a lot of data, but the information is not visible. It's just inside the data. And that's exactly where machine learning, deep learning is playing an important role here. So the capability of extracting interpretable information from this huge amount of data. And of course, this is expensive, requires very high demand, is very high demanding types of computation, is very challenging, very complex. And that's why values is a very important property for defining big data. All right, so this is my slide, my last slide, and basically here I want to like to mention a major activity that we do. We have in Iceland, but I'm also involved with Professor Maurice Riedel, but also two PhD students, Rocco Sedona and Subi Sharma, and this is part of the National Competence Center for HPC and AI in Iceland. And this is the Simulation and Data Lab Remote Sensing, which basically base its work and research activities and the intersection of remote sensing application, parallel and scalable machine learning methods, and advanced computing technologies. And these include high-performance computing, quantum computing, and specialized hardware computing. So this lab cooperates actually with a new working group from the IEEE Geoscience and Remote Sensing Society, GRSS, which I'm leading. And this group is called High Performance and Disruptive Computing and Remote Sensing. Actually, from the website here, you will find the direct link to the website. And together with this working group, we will try also to connect the community of these interdisciplinary researchers in remote sensing in order to disseminate knowledge to educational events, special sessions at tutorials at conferences, and public activities. And we're actually organizing a summer school at the end of May, which you will find advertised on the website. Of course, we're also collaborating with different universities, especially here in Germany with Bonn, Aachen, Berlin, but also outside Germany, like University of Trento, where I actually did my bachelor and master. In joint activities that include research projects, teaching courses, and basically supervision of students. So you're free to have a look to the website and also contact us if you want to join. All right, so thank you very much. I will now go through by the references so that you can see it later on. And I thank you very much for your attention. And I hope to see you maybe next year in Iceland. Thank you very much.
All right, yeah, thank you very much, Gabriele. That was a very useful lecture. And I think we will continue this interesting set of practical lectures with the next lecture given by Rocco Sedona, who then will take care of scaling this really up, doing distributed deep learning at scale. But that's all for today. Thank you very much. Also to Gabriele for the invited lecture. Very well done, and see you next time.